Your online application's starting to fail. It's crawling on the network just as fast as a snail. We need invented programming starting from the top. Better write some code so the world doesn't stop. With the non-blocking model, we will be just fine. Built on Google Chrome's V8 runtime. And all you need to do is write some JavaScript code and use the real-time web with Node.
You're watching Real-Time Web with Node. I'm Carlos Souza, and in this level, we're going to be talking about streams. When we're writing applications that depend a lot on network access and accessing files in the disk, one thing that we have to keep an eye out for is how the data is being transferred back and forth. Lucky for us, this is where Node.js really shines. For ultimate efficiency, and especially when we're dealing with large-sized data that's being sent across the wire, we need to be able to access that data piece by piece or chunk by chunk. When that happens, we can start manipulating that data as soon as it arrives in the server and keep it from being held into memory all at once. Streams are like channels where data can simply flow through. They can be of different types, but we're going to be looking at the two most common, readable and writable streams. And the Streams API that we cover here is for Node version 0.10, also known as Streams 2 API. Some of the code that we've seen in the course has already involved working with streams. The request object, for example, is a readable stream, and the response object is a writable stream. We read data from the request, and we write data to the response. When we run this code and issue a request from the browser, our server responds with a 200 status code and writes "dog is running" to the stream. The browser automatically receives that response. Then, we fire a set timeout for 5 seconds, but the stream is still kept open. The channel between the server and the client is still good to receive data. So 5 seconds later, we write again to the stream. This time, "dog is done." And finally, we close it. We've seen how to write to the response, but how might we read from the request? As we've mentioned before, the request object is a readable stream, and it also inherits from event emitter. This is a great combination because the request object can then communicate with other objects through firing events. The events fired are readable, which is fired when data is ready to be consumed, and end, which is fired when the client is done sending all the data. Now let's write some code where we print to the console the data that we received from the request. So inside of our request handler, we start by responding with a 200 status code, then we listen to the readable event on the request object. Inside of that, we declare a chunk variable. Inside of the while loop, we're going to read out a chunk from the request, and if it's not null, we'll print it to the console. We have to call the toString function because the chunks we get, they're buffers, so we might be dealing with binary data here. Finally, we'll listen to the end event, and when that event is fired, we just finish the response. With this code, we're printing to the console the data that we get from the client. How might we change this so that we echo back to the client the data that we get on the request? All we have to do is change one line. In this case, instead of console.log, we call response.write here. Notice that we don't have to call the toString function. Response.write does that behind the scenes for us. When all we need to do is write to a writable stream as soon as we read from a readable stream, which is exactly what we're doing here, Node actually offers a helper method that we can use to pipe these two operations together. This method is called pipe. Pipe handles all of the event listening and chunk reading behind the scenes. So we can replace all of this code with this one line. Now, when we run curl from the terminal and send in the string hello, we can see that string being sent back. In case you're used to the Unix syntax, then you might remember pipe from the command line, which streams the output of one operation to the input of the next one. Whenever you can, prefer using pipe over listening to the readable event and manually reading the chunks. This can help protect your application from future breaking changes to the Streams API, which is still not stable. Remember that Node itself hasn't reached 1.0 yet, so it's always good to check whether a specific API that we want to use is stable or not, and we can do that looking at the docs. Each core module has a stability score next to it. We can see that the file system module is considered stable with a score of 3. This means that no major changes are expected anytime soon. On the other hand, the Streams module is still unstable with a score of 2. This means that changes to the API are still possible. So next time a new version of Node comes out, it's important to check for any changes on Streams or any other unstable API that your Node application might be using. Let's go over another example of using Streams. This time, we're going to read the contents from a file in the file system and stream it to another file. So first, we require the file system module. Then we create a read stream from the original file, readme.md, and store that to the file variable. Then we create a write stream to the destination file, readmecopy.md, and store that on the new file variable. All we have to do is call file.pipe, passing in the new file. Streaming is so powerful, yet so simple to use with the pipe function that there's third-party libraries that heavily depend on it. One example is the Gulp build system. Gulp exposes the pipe function as its public API, so you can do all sorts of manipulation on assets with very few lines of code. I suggest you check out Gulp's website to look at some examples of using streams in the wild. We can pipe any read stream into any write stream, so let's combine the two examples so we can read from the request and pipe it to a file. So we'll keep our write stream as is, but instead of reading from a file, we're going to read from the request, calling request.pipe and piping the content to the new file. Lastly, we'll listen to the end event and close the response, responding with an uploaded string. Now when we run this from our client, we call curl with the --upload file option, passing in a file as an argument. And then we can see the response back. So let's take a moment to visualize what's going on here, because it's pretty amazing that Node supports this. So we're streaming pieces of the file from the client to the server, and the server is streaming those pieces to disk as they are being read from the request. At no point in time is the server holding the entire file in memory at once. It's all just flowing continuously, and due to Node's nature, it's all non-blocking. So if we try to upload two files at the same time to the server, we can see that our Node server can handle them simultaneously. One of the reasons that Ryan Dahl created Node.js was to deal with file uploads. If you've done enough web development, then you're probably familiar with the whole drama that goes around implementing file uploads correctly. What a lot of web apps will try to do is to load the entire file into memory before writing it to disk, which can cause all sorts of issues on the server side and affect all the other users of that same web app. And it's also tricky to be able to provide the file progress to the clients as the file is being uploaded. In Node.js, we can actually do this quite simple. So let's look at how we can implement our own file upload with progress. So this is what our uploader will look like. We need to be able to issue a request passing in a file, either from the command line using curl or from the browser, and then receive the progress as the file is being uploaded. To implement this, all we need is the HTTP module and the file system module, which we've already been using from our previous examples. So we'll start with our upload code, which we already created. Then we need to know what the entire size of the file is, and we do that by reading the content length header from the request. We're going to store it on the file bytes variable. We'll create the upload bytes variable to keep track of how many bytes were uploaded, and we'll initialize it to 0. Then, listening to the readable event, we'll loop through and read each of the chunks from the request. Inside of the while loop, we'll increment the uploaded bytes variable with the length of each chunk. Then, we calculate progress by dividing uploaded bytes by file bytes and multiply it by 100. Then we send the progress back to the client using the response.write function. We use parseInt to round the progress to an integer. Down at the bottom, pipe is still taking care of the actual upload for us, and the only reason why we're using the readable event is so that we can keep track of the current progress. Now when we run our code and upload our file, we can see the progress. Nice. So that's it for this level. Have fun with the challenges.